بسم الله الرحمن الرحيم ربي اشرح لي صدري ويسر لي أمري واحلل عقدة من لساني يفقهوا قولي. Assalamu alaikum to my dear subscriber. This is a video on railway track design, and I am Professor Adnan Kadir. The contents of this presentation are design standard criteria and approaches that are used for railway track design, the standards for railway design, the design steps, and to conclude our discussion, I have a numerical example to just explain or just to summarize what is being uh, elaborated in the slides. So let's start. Railway design have no standard, single standard. Universally, there are many standards uh, as compared to the building code design where we have ACI. So the railway has different standard. So why? It's because many weights and sections have evolved by the efforts of various designers. One of them is American Railway Association, or branded as RA or RB. So those who have seen the rail section suffix as RA or B, that represents the properties that is being designed by ARA, RA. Then American Society for Civil Engineers, it is branded as AS. The most common standards that are being followed, just like we have an H2 design guidelines of pavement design analysis of pavement H2 1998. So we have in railways, it is AREMA, American Railway Engineering and Maintenance Association, and it was formerly known as AREA. So rail sections adopted from this manual are branded as RE, or so you can say it is RE subscription. Then we have IUC, UIC, it's the International Union of Railways, UIC. Then we have a different designations, sometimes numbers, not letters, depends on the manufacturer. We continue with the design standards. Many railways have several design standards. Differences do exist. Examples, some use 2/3 of the wood tie length in analysis. Some use entire length. Some use entire concrete in the length. Some use 2/3 if it is a concrete tie. Some use a rail seat force as Q naught into 1.5. And in a matter of time, you will soon find out what is Q naught. Then allowable bend stress in rail may vary. Allowable rail seeker may vary and depends upon the wood species. It is between 250 to 400 psi, while AREMA recommends 200 psi. We continue with the approaches, the standards of specification. AREMA says a tie reaction of 65 psi if it is a wood tie, and 85 psi, but some did use both 75 psi, means higher load. Ballast quality and ability to resist crushing forces. Degradation is the #1 cause of the ballast falling. Some railroads use different track modulus values. Sorry about that. What are the design steps? First is we have to know the wheel load based on the most common heaviest car and desired track speed. Consider all wheels in the trucks and approximity of the adjacent car. Then we have to select the track modulus. It is normally symbol as small u or k. It is based on the desired design deflection. Then we have select rail size and section. We calculate moments and loading coefficients. Then we check the rail bending stresses. We choose trial tie spacing, select tie size, check bending stresses in the tie and determine and select plate size based on the minimum area. And determine the ballast surface stress, determine ballast depth, calculate track deflection, and check on acceptability. If the deflection is unacceptable, redo design. Always let it know. So these were the brief steps. Now, in the slides to follow, we take one step, one at a time, and try to know how we determine all those parameters one by one. So let's see. Now, first step one is to know or select the design wheel load. It's a base common as based on most common heavy scar. Depend on track speed as well. We consider all wheels in the train and if there are adjacent cars attached to it. There are types. The loads are categorized into two types, the static load and the dynamic load. Obviously, the main difference between static and dynamic loads is the behavior over time. Railway tracks are designed for the dynamic loads. So let's once again try to know the difference, static and dynamic, although most of you have already known this, but as a novice, you can always go what is the difference between static and dynamic load. Especially those who are not familiar with these railway terms, it's better that they understand these simple concepts. Static load are a load that remains constant, as the word static suggests. Dynamic is obviously it fluctuates with time. Static can be permanent, while the dynamic is caused by moving around magnetic objects. The examples of static load are the weight of the building, stationary equipment, force, load carried by a bridge when no vehicles are present. And as you can see, as you can think, the dynamic, the load from vehicles or moving vehicles, wind, waves, earthquakes, or cyclic events. Static loads are predictable and they do not involve any sudden change, while dynamic load always add complexity like frequency, amplitude, duration, and resonance effects. Don't be worried, we are not going to too much detail while calculating the dynamic load. We just have to use one relation that will be explained here. If you know the wheel load, all you have to convert in dynamic load, you just have to use this relation P plus theta P, and this relation has been obtained from AREMA. PV is the vertical dynamic load. Theta is diameter of standard wheel is in a rail train is considered as 33 inch. So dia of 33 inch into velocity at the speed, then the dia of a given wheel that you are using, the traffic you are considering in your design, multiply by 100. Wheel diameter, speed in miles per hour, P is the static load. See that larger wheel impose lesser. Now, additional dynamic loads, while considering, is being ignored in this analysis. And one would, let's see how much we have: 33 inch, 36 inch, 38, 28, 36. Now, if you have all this mix of vehicle, so what wheel load we are going to use? This may be your question. For instance, we may have a weak train traffic or train traffic, we can say that it has got 28 inch. So while calculating dynamic load, we'll use least of the diameter as given as we have the vehicle. So you can think of a higher dynamic load. I think I have clarified that if we have all these configurations available, you are while for calculation, you are going to select the least diameter. Now, step 2 is to know the stiffness of the track. For that, we know or we assume that rail is a beam on an elastic foundation. Its track modulus, also known as track elasticity, can be calculated with a simple relation U is equal to load over unit deflection. Modulus of track elasticity is pounds inch per inch per inch. We all know what is P, and we know unit deflection, and it can say less play or track looseness. More deflection means loose track, less deceleration means a tight track or less play. You can also calculate U from this relation. Instead of having delta, we can use the die spacing between the sleepers. Now, again, the question, what will be the fit? Again, we will go for the higher of these two values. Now, some people have recommended that these values are acceptable. For example, if it have a wood tie, we can have 3,000. Concrete tie, 6,000. If you have tamped the wood tie, it's 1,000. And wood tie with frozen ballast, 9,000. On concrete, it is 12,000 pound per inch per inch. It can be pound per square inch, but it's not. It's pound inch per inch per inch. So remember this thing. Select rail size. Now, depending the rail section, it depends upon many factors. That is the type of track, the expected load, train speed, and industry standards. Heavy track, we can use 136 RE, 145 RE, 1 RE or 155 RE. And RE is for, area. Then light rail, we can use 30 kg rail section, 40 kg, let's say 40 kg per meter. And then the first one is 136 pounds actually. And then lighter section designed for lower loads. Then for industrial, it depends upon the loading requirement. And we have a rail size other than that is normal. Then this curved track, it again depends on the curvature and expected loads on the track. Specialized rail sections designed to accommodate and provide smooth transition. And now for high speed rail, generally largest rail sizes are used that are the sections that are designed to minimize vibration, provide stability, and ensure passenger comfort. Normally, if you select one rail section, for instance, 133 RE, then you have different values like 133 means 133 pound per yard weight of a section. Its moment of inertia is 86. Set neutral axis is 3.20, section modulus 27, area 13, height 71.16, base width 6, head width 3, and head radius 10. All these are the inputs related to different. Now, uh, look at this table. You can see that as we go for the lower weight section, all these values are decreasing. This is what we can infer for this table. We continue. Once we know your real sections, then we'll have to know your moments, the moments in the rail. It can be calculated from this relation 0.318 E times x1. Deflection from this relation and rail seat load, also known as F maximum, can be calculated from this one. Now, you can see from serial 1 to 2, 1 to 3, there is an unknown that's x1 and x1. You need elasticity modulus, moment of inertia of the rail section, as well as the track response U that we have discussed previously. We know that B, what is B, what is U, what is S, is a die spacing, and the modulus of plasticity, and now the step 4. If once one is want to know what should be the value of Q naught, load sitting value, the maximum value is, for instance, if we have 6,000 U value or K value, and for 132 rail section, it can be as high as 8239. And in percentage of P, it is around 28% of 27.5 to be exact percent of the load. This is how we verify your seating load. Now, once you know, then you have we calculate the rail bending stress. One simple formula, always being a civil engineering student, 1,000 times we have used this formula. So I'm just going through it. No need, I think, for similar. Now, for railway, it is good if we have a jointed rail, we have a 32,000 psi allowance. So maximum stress, if it is beyond that, then we have to may do something with the rail section or rail design, and 25,000 for CWR or continuously welded frame. Now, how you will find the bending stress? We can use this force diagram like that, like this, or we'll have pressure distribution and principal superposition, and there with this simple relation we can find the center movement and the reactive movement based on these equation and this relation. Now it is understood that the maximum rail bending stress is between where the two vehicles of the trains are joined. These are the point where we calculate the stresses, and the moment location is as shown. These are the larger width, or you can say from that it is from second axle after the connection, and you can calculate maximum bending moments. The first one is to know where rail seat reaction will be from the first wheel, and while the bending moment reaction will be on the from the second wheel. Now, mathematically, you can calculate this maximum bending moment using this equation. Increase height means greater I, but we have to have a ratio, web height to thickness ratio. It is around 1.5, I guess. Maximum bending stress less than or equal to allowable bending stress. Now, then we go for the analysis of the sleeper or tie. Uh, it's the first thing, it was believed that all the reaction is uniform like that. But then the Delbert found out that this is more concentrated on the uh, area near the seat load, while it is less concentrated on the center or the cantilever portion of the rail section or tie section. We continue with this. So again, to know the bending moment, we need to use this stresses actually. This is the same thing. Now, obviously, these moment of inertia and all those modulus have now been used for the tie section. Oh, sorry. It says that wood, it can be for different material normally, but oak weight is used. So let's think that we have to compare. We have a maximum value of 1400 psi. Again, if you know what should be the optimum length, so you can always know your MC and you always know your MR. And then if you know your material, this is for yellow pine, you can always know what it should be the die length and fit. For instance, here it can be at 8.5 inch. Normally we have 8.5 feet, I'm sorry. Normally we have a 9 feet die, wooden die section for broad gauge. Now, the load distribution for the plate, 2/3 of the tie length is involved, and unit weight on thus will be 2 times Q naught over A dash P, or thus PA is equal to 3 times Q naught over L, where PA is the unit tie pressure of the ballast. This is 65 psi for wood and 85 psi for para. A dash B is total tie bearing area. L is the tie length. B is the tie width in inches. And Q naught is the rail load as calculated. Now we can have a plate analysis. We have two different types, single shoulder and double shoulder. Width of the size to fit the tie. Length to keep stress on wood tie less than 200 psi. So stress is Q naught over P naught. Q naught. Stress is Q naught over plate area. Distance between shoulders, space to match rail base width. Now, AREMA has given this this way or this formulas to know your depth for ballast. And this is the typical rail section you must know and must have known by this lecture, before this lecture. And then you can see this typical Bosnian equation and how this Gaussian distribution is there to explain the distribution of load from time. It's a sleeper shown here, you can see, to the underground ballast or the low base, like not underground, it's the under ballast field. So ballast depth, we can have different ways. One is to use this relation 16.8 P over PC, you have to raise 4 power 5, where H is the support ballast depth, stress at the bottom of the tie, PC allowable subgrade stress. And this distribution is independent of material. Then we can have Allowable subgrade can also be calculated from Japanese linear equation. Gaussian equation can also be used, and there is a scientist known as Nerve. It has its own, he has its own formula for calculation, where R is the this thing. The last equation, R is the radius of rotated circle, whose area equals the effective tie bearing area at the workpiece. Now we go off the ballast versus subballast. Subballast can be a new construction or reconstruction. Generally, half of overall base ballast should be highest quality available. 6 inch is the minimum depth of the subballast that is provided. Every roll have their own values that may be minimum of 12 inches as well. Some require 12 inch. It depends on the existing track. All or some of the old ballast layer becomes new ballast layer and new ballast added. But old material likely to be marginal quality. Bottom ballast and subballast differentiation becomes blurred. Ballast layer often described as a top ballast and bottom ballast section. The top ballast section is normally a damping zone. Now, you know typical values, the additional values for the allowable subgrade stress is 20 psi. AREMA requirements 25 psi. It is using soil strength with a factor of safety. So for that, AREMA recommends at least 2 as much as 5, depending on the traffic wind load. Company design standard will dictate how much load. For normal tracking, it's a 5 million gallons, 5 million gross tonnage per year. It can be 1 or 0.8. It's a bearing capacity if it is 5 million gross tonnage unit. A scientist here recommend a factor of safety of 1.5 and 2.5, thus allowable stress as less than 1.67. And this is a table that can be used to know allowable subgrade pressure BC. And for instance, if you have a fine sand, it can be as high as 25 and it can be as low as 15 in PSI and 60 to 100 in kilopascals. Then the trap deflection, these are different category. So if the range deflection calculated deflection is range between 0 to 0.12, it's a very good track. It will last many time. And then normal maximum track between 0.12 to 0.25. So it's a B, it's a normal value. C is the limit. So if any track system track that is past 0.36, it means it has already failed. So no track must the value of deflection on any track below 0.36 doesn't represent a good picture. And if it is with a zone of 0.40 to 0.5 and above, then it's a poorly maintained track and it is likely to deteriorate quickly. Now let's summarize what I have explained in terms of a numerical problem. We have to verify a track system that is following input. And this is the train that will be used, the loading. It has a load of 22.86 tons, as you can see, wheel load. It has been given a speed of 120 kilometers per hour. Since it's a wooden Sleeper, we are assuming 3000 psi, or not psi, it's pound per inch track modulus. Then rail section, it's not 136, actually, it's 133. I've used it. Then there's a tie 7 inches into 9 inches cross section and 9 feet. So let's summarize the inputs uh, in terms of units that are being needed in our analysis. So what I've done is just making these units compatible to our equations. So it's just, we have 50 load and we have speed and the track modulus, the properties of rail section, and then this rail. You can always go there to know. From here, I'll get this value and then I'll go back there. This is the wheel die is 38 inches. This is given to us. The spacing of die is 20 inches. Again, this is an input in the numerical function. I have not assumed anything there. I've assumed this data actually. It's an hypothetical problem. And there's largest modulus of steel is 30 million psi. We all know that. Then we go to another detail. The slipper, it's 9 feet length, 108 inch. I mean, width 7 inches, height 9 inches. And these are the properties obviously calculated from these values. Length of the broad gauge, length it was assumed that it's a broad gauge section, and the plate size is again given to us. Now, step 1 is the wheel load design. We know this relation, and this is just a routine calculation. 33 is the standard wheel, 38 is the given wheel, so this theta is 0.65. So what we are going to do is to enhance the load, static load by 65%. It means the 50,760 pound is actually 83,822 pound dynamic load. This is the step 1. We move to step 2. Step 2 is about track modulus. We don't have to select. It's a put-in track that has been given to us. And again, that was explained in the slide 15 of this lecture. We have to select rail section. This is an input already known to us. So we don't need any selection. And we can always assume that trial section, but since it is given, so we are not going for that. Therefore, we know that this is how the rail section look like, and you know where have this value been calculated, when has that been obtained. Then we have to find moment of coefficients already given to us. And for our problem, the wheel load we have calculated step 1. We track modulus we know. Die spacing we already know 20 inches. So we can calculate x1 from the relation given here, and consequently we will find the rail movement as 674,674,676 pounds inches, deflection 0.431 inches, and rail suit load as 25,887 psi, you can say. Sorry, pounds. Then the step 5, rail bending stress. We know this equation. And obviously, from there, to find the value of 674,666. Just plugging in the values we have calculated above. C is the stress, and then the stress can be calculated just from these calculations We know that m naught is, we have already calculated the previous step. Z is simply moment of inertia about divided by c. So that's how we calculate the stress in the rail is 25,104 psi. Now we go from 6 to 8. Now we are talking about the ties. First, we were calculated previously. We got calculating the stresses in rail section. Now we are going to calculate stresses in die section, and this is how the relations are given to us. So we know we have just plug in the values calculated previously, and we find this value, and ultimately you can find at the bottom the stress in our tie sleeper comes out to be 1643.63 psi. I hope I'm not going very fast. It's just plug and play equations, and you will find the values. Once the bottom line is that once you know these steps, now in solving the problem, you just have to go through the steps one by one, and you find the solutions. Now we know that how this plate load is designed, as you can see, and for our, we have already been given, and slide 39, the plate size. So we can calculate the, we know our area of the plate, and we can always find out the PA. Unit die pressure as 102.72 is. Now, depth of the ballast, we use Talbot equation. PA is calculated, and PC we have calculated. Sorry, PC we have calculated from this value. We know that it's 25 is sorry. From that, we know that 25 is there. You can use this thing, or you can either use this equation, this table to find PC, and once you know this, you can find it to explain to get back where I was. So we know PA, we know PC, so our ballast depth is 29.6 inches. Ballast surface stress, we use this Bosniak equation, and we know that our stress is 286.62 psi. We need to know the deflection, we already calculated. So you can use this equation, and our deflection is 0.431 inches. 0.431 inches. Now let us analyze what is this. So if we know that we have calculated stress as 25,104. The specification says if it is jointed rail, you are allowed 32,000 psi, and if it is a CWR, it is 25,000. So if we can say that if you have considered this continuous welded rail, the value is theoretically inadequate, but still it is valid for jointed rail, but not for continuous welded rail. Let us look at this stress in ties. So that is 1643. What is allowed is 1400. So obviously our ties are not adequate. Again, since the ties is not adequate, the deflection is dependent on it, and it's 0.431. And it comes, if we have referred to that slide on 36, we find that it comes under T. That means if we continue with this tie, a wooden tie, our section will soon fail. Again, this 102 psi we have calculated. We have allowed less than 65. So it's an inadequate. In the depth of the ballast, minimum is 12 inches. So it's okay. We have a depth of ballast 29.6. To conclude this numerical, we can say more or less our stress in rail section is okay, or we can say 133 pound rail, a pound per yard rail. But what we need to do is to change our ties, and obviously nowadays we are going for that as well. So instead of using a wooden tie, we can use a concrete tie, and that will again, if we use that concrete tie again, this will not only results in the lesser values, lesser stress in sleeper, and or to also control the deflection, because the value of stress in the sleeper is deflection value of deflection is depend on the resistance of stress of the sleeper. So if we use a more good sleeper, then we'll have less deflection, and so is the value of unit die pressure will also depend. So that's it. Thank you very much for listening to this lecture. If you have query, you can always write down at the bottom of that. So thanks very much. Take care.